Wireless LAN Professionals Podcast, episode 143.
Wireless LAN Professionals is a place to educate, inform, encourage, and entertain those involved in wireless LANs. This Wireless LAN Professionals podcast is an audio manifestation of these goals. Our host is a wireless LAN veteran, consultant, designer, and teacher, Keith Parsons. And now, the podcast for wireless LAN professionals by wireless LAN professionals.
Hi, Keith here again with Lee Badman today. Lee, how are you doing?
Doing well, Keith. How are you?
Very good. Glad we could get you on. This is being recorded before, but we'll probably be broadcasting the podcast afterward, after WLPC. I thought we could just get together with you for a little bit and talk about your deep dive session at WLPC.
That sounds good.
Great. What is it?
Well, we're going
for those who aren't coming, let's kind of bring them up to speed.
You're saying there's people that aren't coming?
I've heard of a couple, yeah.
Do we even care about? No, I'm kidding. So we're going to be talking about the introduction to pen testing, and we're going to be wireless pen testing because it is the Wireless LAN Professional Conference. So even though it's wireless pen testing, we can't help but kind of drift off into the rest of the ecosystem that wireless works in. But it's going to be done with the assistance of the Pineapple Tetra from Hak5, which is one of their two latest. It's a dual band little wonder box. And
so what's the difference between the Tetra and the other box?
The Tetra is a dual bander. The Nano is a USB, you plug it right into your Mac or your Windows, but it's a single band, smaller unit. But basically, it's the same code underneath, the same operating system. It's going to be a different class of hardware. All the specs are online and all that. But little versus big, dual band versus single band, and we're using the big one.
And the big one has how many? What are there? So it has a one radio for 2.4, one radio for 5 gig. What else does it come with?
It also has a variety of power options, and it's got a USB adapter for an optional but highly recommended third adapter, and we're going to be making use of that at the conference. Also has a serial cable connection, and basically anything you'd get in a kind of a low-end business-grade wireless router, I guess is a good way of thinking about it, but it just does a lot more than that.
And we opted this time to go with the tactical package, which means it comes with a bag and actually a very nice little Anchor battery to charge it with.
Yes, and it does last a good long time, I've learned. So the bag is another Hak5. It comes from Hak5. It's part of their set, like you mentioned, the tactical kit, and it does make for a really nice little package. They give you a couple of stickers. We also have a very nice book that goes with it too during the conference. And so you put it all together. It's a really nice package to walk away from the session with.
And literally walk away and do hacking as you walk.
Now, hopefully you do it responsibly, and that's part of what we'll be talking about.
Nice segue there. What are the other things we're going to be talking about in your session?
Well, the whole notion of, pen testing, at one point sounded very, very exotic to me. It conjures up images of hacking and cracking and all kinds of spooky stuff. And, if you're not familiar with, being engaged to do pen tests, you might not realize that there's actually very, very specific rules. And we're not going to spend a lot of time talking about the administrative side and the rules of engagement, but we will at least, make sure that anybody in attendance realizes that, we're going to be having a lot of fun in the session, doing some of the exploits and the attacks that you can do with the Pineapple. But at the same time, if you were to do this out in the real world, either for your own organization or for hire, there's very much controls that get put on it, and the term rules of engagement and scope and all of that. We'll be getting into that a little bit as well.
Yeah, I remember when I used to do some pen testing, there was a simple rule that was the difference between hacking and pen testing is just one word: permission.
Yeah, there you go.
And if you don't have the permission, then you're just doing something illegal. But it's still fun either way. That's just how it works. So what are the exercises we'll be doing with our little Pineapple toys?
I don't want to name them all specifically, but we will be.
General categories.
Yeah, exactly. So it's a complicated device. It's deceptively complicated if you're not familiar with it. Once you get a handle on it, it's like, okay, I get that, and I get that, and I get that. But if you're new to it, and I'm assuming a lot of people are going to be new to it, the device itself, you need to get familiarized with it. Otherwise, you're just going to get lost before you start doing some of the other things. So we're going to spend a little bit of time getting to know the device itself without being too silly about that. But at the same time, it is going to be time well spent to actually understand this magic box that we're going to be using. Once we get a handle on the box itself, how to upgrade it, what the different interfaces are for, how to power it, and the options there, how to get it connected to the internet, and the many options there. Once we get past all of that, we're basically going to do things that kind of fall under the broad category of reconnaissance and just, using the Tetra as a tool to see what's around you of interest. And then from there, think of that as, gathering potential targets, if you will, or something in that spirit. Then we're going to get into some exercises that let us manipulate what wireless users within range actually see and how they're, how we can change their perception of reality based on what we do in the Pineapple, a little bit of deception there. And then, finally, within the time allotted, we're going to spend some time actually manipulating the environment, actually making changes that are active. So we've got a component where, again, familiarization with the box, kind of some passive but very interesting stuff, then some, kind of monkeying around with people's minds and making them see things that really aren't real through the lens of their wireless client utility. And then we'll actually get into manipulating the environment and quote unquote fooling people into doing things that they probably wished they hadn't done at the end of it.
Well, sounds like a fun little session. It's actually broken into two sessions, one on the first day, 90 minutes on the first day and 90 minutes on the second. So hopefully people will be kind after they learn how to use it without in the hotel over the first night.
I completely agree. It could be utter chaos. You will find out who the gentlemen and gentlewomen are among us. And those will be the ones that actually follow the instructions of please don't go screw up your fellow man's evening. But I have no doubt there'll be a couple of rogues in the mix, and it's all good fun, hopefully.
Maybe we'll have to do a little like fox hunt and find those bad people and bring along a taser or something.
There you go. I like the way you think.
Well, I appreciate your time here today. This was just a little tease. For those of you who are attending WLPC, if you signed up for Lee's session, you're going to have a great time. If not, we will have them recorded. And you could obviously get your own Tetra afterward and play along at home if you weren't able to come. So thanks, Lee. Thanks for documenting this up and preparing for this session at WLPC.
My pleasure, Keith. Looking forward to it, and thanks for having me.
Main session.
Well, good morning. My name is Eldad Perahia. I am now at Aruba HPE, and I was asked to give a talk on, to give everyone a sneak peek at the next major amendment coming to .11, which we're going to call 11AX. So around 2013, while we were wrapping up 802.11ac, we started looking forward to what problems we were facing with existing Wi-Fi networks and what we thought we were going to face in future networks. So we were getting reports that with networks were still having a preponderance of short data frames, and we weren't capable of aggregating those frames like we did with 11 and 11ac, so it was still causing a lot of efficiency hit. We were seeing networks like this, which you have really dense deployments, so again, different than, say, perhaps the more modern enterprise or home networks that were less dense. So we wanted to look at that. Again, with dense deployments, overlapping BSSs were impacting potential increase in capacity, so we wanted to look at features that perhaps would unlock that capability. And with the whole discussion of 5G and so forth, we wanted to be more competitive with outdoor cellular. So there was aspect of the group that wanted to purposefully address outdoor. So from that through 2013, 2014, the study group came up with a list of goals for what would be the 802.11ax task group. We were going to enhance operation in 2.4 and 5 gigahertz. As we all know, 11AC was only in 5 gigahertz, so we haven't had a major enhancement at 2.4 since 11N. So we were going to go back and actually try to improve 2.4 gigahertz as well as best as we could. Still, major focus is on 5 gigahertz, but we're not excluding 2.4 this time around. 11N and 11AC focuses on throughput, on aggregate throughput. You can always trick this by, if you have 100 clients, you can just not serve 99 of them, serve one client, and you can get really high aggregate throughput. But that doesn't give you very good average throughput across the BSS or the cell, right? So we're going to focus on average throughput per station. We're going to try to get 4x. Hopefully we're going to have enough features in 11AX to do that. We're going to, as I mentioned, look at environments indoor and outdoor this time. And we're going to have a wide range of scenarios that we're seeing a lot of dense deployment. So, increase in density in a corporate office, outdoor hotspot, apartment buildings where you have dense deployments and nearby residential, and stadiums. Stadiums we're seeing a lot of Wi-Fi deployment stadiums, and those are really problematic. And as usual, any major amendment, we try to improve the power efficiency at the clients. Okay, so before I actually get anything technical, most people ask, when's this coming out? So I'm going to start with the slide of when it's coming out. So I did two things here. I have the official timeline, and to just see how much, how fanciful that is, I actually put the 11AC timeline. So we had the task group kickoff in May 2014. For 11AX, we did things a little different. There was each amendment, 11N, 11AC, there was a special interest group got together and started brainstorming. You see in 11AC, it started well after the start of the task group. Well, this time it started beforehand. But it took them a long time to get to draft 0.1, right? So that's just going to give us an idea of the realistic timelines here. And then from 0.1 to recently 1.0 took them quite a long time. So even though the task group appears to be working kind of in line with the time frame of 11AC, it's actually taking a lot more time. And we're going to see that because there's a lot more features in 11AX than there were in 11AC. 11AC essentially did Downlink Multi-User Mimo and did 80, 160 megahertz channels, but nothing theoretically more interesting than that. So 11AX, we're going to see a lot more features. It's just taking a lot of time to craft. Let's see. So we're predicting May for 2.0. That's never going to happen. Hopefully, there were 7,000 comments compared to 11AC, which had a couple thousand comments in draft 1.0. So if you look at how long it took to take 1.0 to 2.0 for 11AC, well, so 1.0 hopefully maybe to get the comments done, I don't know, maybe in the fall. So this is, we were predicting a faster schedule on 11AC to be done by the end of 2018, but it's somewhere we're looking at 2019. That said, we've seen now for 10 years that when the standard finish has really little relevance to when the products come out. So 11N draft products came out at 2.0, 11AC came out at 3.0. So Wi-Fi Alliance is already starting the process of developing a certification plan. Hopefully 2.0 and 3.0 will come out somewhere the first half of 2018, the spec, and then we can be certifying somewhere, we're targeting 2018, but probably early 2019. Because if again, now we look at the Wi-Fi Alliance certification plan, 11AC took about 36 months. So the same time would put us kind of the first half of 2019 to have a certification plan. I'm a little concerned this may slip as well because the number of features are much, much larger. And so the amount of tests that need to be developed is going to push it to be much longer than a certification development plan for 11AC. But hopefully somewhere in the first half of 2019. Okay, so I keep on mentioning how many features there are on 11AX. So the problem with trying to present it is how do I group this such that we can kind of get a handle, rather than a list of 100 features? How do I put this together so people can kind of get a feel for what we're trying to do? So I tried to bucket the major features into categories of enhancements. So like 1111N and 11AC, we have spectral efficiency and throughput improvements. That's the upper left corner. Then to address density, we have features that are specifically introduced to address high density. We have the outdoor longer range category, and then we have the power saving category. And we'll go into a little bit of detail since this was like a 3-hour presentation that I cut down to 1 hour. So we'll go into a little bit of detail on each of the main ones. But as a kind of high level overview, we're in terms of kind of raw throughput. I took some liberties of putting 8x8 AP here. You could actually build that with 11AC. It wasn't very prevalent, if at all. We will be seeing 8 and 10 11AX devices. We've allowed Downlink Multi-User Mimo to go up to 8 clients, so you could really make good use of those 8 antennas. So I'm calling that a 2x improvement for 11AX over 11AC. We're going to increase our modulation to 1024 QAM. Raw data rate, we could discuss how much range you get and so forth, but raw data rate, that's 25%. We're gonna have Uplink multi-user MIMO. So in 11AC we only had downlink. We're gonna have Uplink now. We'll talk about that. I'm gonna skip the OFDM symbol for a second here. So the next category is high density. So we have OFDM as our basic modulation scheme for decades now. We're going to do OFDM access. We're going to split up subcarriers within a waveform to a bunch of different clients in parallel. I'll have slides on that. That way we can transmit to more clients in parallel and get efficiency improvement. I'll talk about that in a second. Because of that, we had to change our waveform structure. So the waveform symbol length increased so we can get more subcarriers. We then made it more efficient. The preamble is now more efficient. The subcarrier count is more efficient, so we're going to get a raw, just by doing the changes for OFDMA, we're going to actually get a data rate increase. So that's why long OFDM symbol straddles spectral efficiency and high density. I talked about overlapping BSSs. We're going to have a spatial reuse capability such that we can purposely reuse spectrum and treat it as not interference, or rather than defer, we can treat as interference and then transmit over each other and hopefully increase capacity. Next category, outdoor longer range. We're gonna, since we have this long symbol, we can actually have longer guard intervals without hitting our efficiency. So we can increase our delay spread protection. We have a new packet structure that we've specifically designed to provide extended range. And then the last category is power saving, and we're going to borrow a feature from 11AH. That's, I think, recently completed amendment to target IoT and 900 megahertz band. You're going to hear me talk about that. we can argue about whether that's actually to be used or not, but a lot of the features they added in AH we're going to borrow in AX. So in that sense, it was a useful exercise, whether or not it actually gets deployed. So we have a schedule sleep and wake time function in AH that we're going to use in AX to reduce the power consumption for devices that want to stay asleep longer. And if you recall, in 11AC, it was required for all the client devices to support 80 megahertz. We did that to just mandate higher throughputs. We're going back on that. We're now in AX, we're going to allow 20 megahertz only devices. Again, cost and power saving. So there's a 20 megahertz only feature as a kind of subclass to the clients. So that's the high level overview. We're going to touch on each of these features a little bit more in the upcoming slides. Hopefully I don't run out of time before I reach all the features here. Okay, OFDMA. So this is kind of one of the big new features for .11, and we're introducing this to improve efficiency. So the biggest issue we're seeing with efficiency is when we have a whole bunch of short packets that we can't aggregate, then you get a lot of, so you get a lot of clients transmitting short packets. The preamble is really, overhead is really high, right? If you're 80 megahertz wide and you're sending 100 bytes and you just got a couple symbols, I mean, your data isn't much, your data time on air isn't much longer than your preamble time. So half your efficiency is gone just to the preamble. All the contentions, interframe spacing, that really hits you badly if you, again, lots of short packets, a lot of users, and you spend half your time just contending for the channel. So that's so that's kind of the main issue we were trying to address with OFDMA. So we tried aggregation 11N. So packets that can be aggregated from a single client, that's great. We can get packets up to thousands of bytes, get the packet length up to a millisecond. That works really well. What do you do with voice over Wi-Fi, right? I know in my home I have no cellular coverage. Work, I have no cellular coverage. Most of the hotels I've stayed at, I have no cellular coverage. I'm almost 90-something% on voice over Wi-Fi. So problem is, if you don't want to kill your latency, your jitter, stuff like that, it's really hard to aggregate these 100-byte packets. So if you get a lot of people on voice over Wi-Fi, say corporate enterprise, you just have horrible efficiency. We did Downlink Multi-User Mimo. Okay, so we have a lot of users. We want to group some of them together. That improves efficiency. That also still works best, say, with video streaming or somewhere you have a constant stream of large packets because you have the feedback that you have to amortize over your transmissions. So we did time, we did space. Now we're doing frequency. So I have a little plot of here's a kind of a typical OFDM transmission that we have in .11. You have a data preamble. This is pretty much the scale if you have a really high data rate and short packets, right? So you spend an enormous amount of time on preambles and on contention, right? So if we can divvy up our frequency band into say this is 80 megahertz and you give 30-some clients each couple megahertz, right? Short packets. So it's not a big deal, right? You don't need 80 megahertz to transmit 100 bytes. So then you can get all of these clients, users into one packet, and then you amortize the preamble. You get rid of 30-something contentions. So you can group all of these acknowledgments into one multi-user block ACK. Right, so you have the potential for pretty high improvement in efficiency. And again, so what we're going to have is a big toolkit of features that the scheduler, or the AP, or the controller, or the client have to figure out what feature am I going to use when. Am I going to use aggregate 11N aggregation? Am I going to use Downlink Multi-User Mimo? Am I going to use OFDMA? So at least we have a whole toolkit on kind of optimizing the technique for the environment. So we're going to introduce OFDMA on the downlink. So the access point when transmitting to a lot of clients can utilize this function. Unlike 11AC, we are also going to do this on the uplink. So we're going to do uplink multi-user capability. So on the uplink, we're going to be able to group multiple users together. I'm going to talk about a couple of different scenarios where we have to synchronize all these clients together. So that's the big complication. OFDMA itself isn't new. I mean, new to .11, but it's not new. But the complication there is the synchronizing all the clients on the uplink. We're going to have to do that for OFDMA. We're also going to have to do that for uplink multi-user Mimo. Another cool trick with OFDMA is you can optimize the power on each individual client to kind of balance or maximize your SINR per user. So you can play with power across the band, right? If you have one user is kind of close up, you can give it less transmit power than a client further away. So we're going to make use of that as well. Okay, so I took one example, 80 megahertz BSS. This is the different resource units that are going to be capable of using. So we have the non-OFDMA. We're going to do a 1024 point FFT in 80 megahertz. We'll talk about the new waveform design later in the PHY section. So we have a 996 tone waveform. This is approximately the full 80 megahertz. Then you can divide it up down to a 40 megahertz resource unit. That's 484 tones. There's a 20 megahertz resource unit. There's an 8 megahertz resource unit. There's a 4 megahertz resource unit, and then the smallest is a 2 megahertz resource unit. And so in 80 megahertz, we can have 37 of these 26-tone resource units. So you can get as many as 37 clients in parallel in a single packet with OFDMA with 80 megahertz BSS. Now you can mix and match these resource units. I mean, the trick is you just can't overlap resource units in frequency here. So you can have a 40 megahertz here and then any combination over there. So it doesn't have to be uniform. You can pick any one. So you can mix and match like a video client with a bunch of voice over Wi-Fi clients. I have a slide next that shows a couple different examples, right? So again, this is 80 megahertz. We have a 40. We have a 20. We have this looks like an 8. A 4 and a couple 2s. Here we have a different assignment. This is 16, right? We have a couple 20s, an 8, a 4, and a whole bunch of 2 megahertz clients. So the key here is as long as they're not overlapped, you can do any arbitrary assignment, and it can be from packet to packet. You can do different clients, different assignments from packet to packet, so it's very flexible in that respect. Okay, so what is the gain that we expect from this? This was some results from a presentation back in 2014. So we won't look at the exact details of the simulation because it's this was before we haven't had an initial draft. But this just gives you an idea of the gain we expect from the general concept of OFDMA, right? So the simulations show, when you have a lot of users, just kind of vanilla OFDM throughput compared to an implementation of OFDMA, this presenter showed a 300% improvement in gain. And so it kind of matches what I showed here just visually, right? You get rid of the contentions, you get rid of all these preambles. You can kind of see that, if you can get a handful of clients aggregated together and you can group all their small data packets, that you can easily see you can get rid of a lot of the overhead and you can get the 300%. So this is our our goal was 4x. This is kind of the 3x part. We need another x. So we're getting close just with OFDMA. Okay, so next is multi-user Mimo. We had this in 11AC. We're going to enhance it in 11AX. So when we started with 11AX, we're like, okay, so how is 11AC working? We kind of introduced Downlink Multi-User Mimo and 11AC back in, I don't know, we were thinking about it in 2009 or something. So we've had a number of years to think about it. We've had some products finally out. Wave 2 came out, so we've had some experience in the field a little bit. I know, I've seen a lot of clients, single antenna. I've also seen some clients that are 2 antenna and switch to single stream when they do multi-user MIMO. So, if you're going to have a 4 antenna AP and a 2 antenna single user client that only then switches to single antenna, then the gain for multi-user MIMO is kind of modest. So that's where going up to 8 antennas now you can start grouping a lot more clients together, right? If you only have, right, with two antenna clients doing 2 streams, well, 4 antennas and 4 streams is kind of marginal. It's nice to have an extra antenna for diversity. So 8 antennas allows you to do, say, 3 clients, each 2 antenna to do 6 streams, or say 6 clients, all single stream. Then you can really see some large, downlink multi-user MIMO gain. Now with that, more clients means more overhead, right? We got to feed back, all the channel state information, right? So we need a better way of getting feedback so it scales with the increased number of clients. The other thing we saw was, well, you can be, big file transfer on the downlink, but then you're kind of blocked with waiting for the TCP-X on the uplink, right? So in 11AC we didn't have anything to enhance the uplink, so we were seeing, so if you compare UDP gain between single user and multi-user, downlink multi-user MIMO relative to TCP gain, the downlink multi-user MIMO with TCP gain was actually smaller, right? So we want to address that. So uplink techniques will help balance the downlink, enhance downlink multi-user MIMO. So again, back in 2008, 2009, when we were discussing multi-user MIMO and 11AC, we did discuss uplink multi-user MIMO. There was quite a number of presentations on it if you go dig around on the repository. But it wasn't, we didn't include it due to implementation concerns. I kind of hinted at that. You need to synchronize all the users, and people were kind of scared of that. Now with doing uplink OFDMA and uplink multi-user MIMO, so there's a lot of potential now, to try to overcome the synchronization issues, right? So it's not just one feature. We need the same synchronization for 2 major features. So with that, 11AX is going to include uplink multi-user MIMO. We can use that for grouping sounding frames to help downlink, data frames, and we can, just like in downlink, we can do that in uplink. We can group multiple users together to increase, the maximum throughput. So OFDMA is about improving efficiency, but uplink multi-user can improve maximum data rates. So that's a benefit there. And then we change, we're allowing groups up to 8 clients. So now even if with single stream, single antenna clients, you can group up to 8. Probably we'll do up to 6, right, to save a couple antennas for diversity. And so then you can get upwards of, say, 6x increase over single user, and then probably a 2x increase over 11AC multi-user MIMO. Now for in the downlink, and then uplink will be new. Okay, so this is the one and only slide. I have a mathematical background, so I like to throw one slide on math. I'm not going to make you analyze it much. Basically, what I wanted to show is that the mathematical construct of just plain vanilla MIMO, right? You have a 2 antenna client, you have a 2 antenna AP, you have paths from each antenna. You get your Y equals HX plus noise formulation. So uplink multi-user MIMO, say you just separate those 2 antennas into 2 different clients, that's uplink multi-user MIMO in a nutshell. And the math doesn't change at all. So my point here is that uplink multi-user MIMO is mathematically equivalent uplink single user MIMO, right? Because we're used to thinking about downlink multi-user MIMO, where you have to do feedback, you have to calculate antenna weights. It's really complicated. This is really simple mathematically, though the problem is it's a lot harder to implement in practice, because to actually achieve this equation, you have to eliminate all of the mismatch in time synchronization, frequency misalignment, power normalization, right? Otherwise, you have a lot of other variables in this equation to model the time errors, frequency errors, power errors between the clients in the group, right? And the downlink, AP sends to, AP has this entirely, has a single clock, power amplifier, everything's nice and pretty. Uplink, every client's different, and so we have to do a lot of effort in just synchronizing. But the math is really simple. So we're going to have a protocol to address this for both uplink OFDMA, because it's the same issue with OFDMA. You have multiple users in the same group with different sub-carriers. They need to be frequency aligned, they need to be time aligned, they need to be power aligned. So we need a synchronization scheme for both OFDMA and multi-user MIMO, and so then we took it on finally in 11AX. Okay, so what does the protocol look like? So this is the uplink multi-user operation. This applies to both OFDMA and multi-user MIMO. So we're introducing a new trigger frame, so a new control frame. It's called the trigger. It specifies the length of the uplink window. It specifies the users that may send during the uplink window. It allocates the resources for all the PPDUs, the packets for each station. So it's the resource unit if you're doing OFDMA. It's the spatial streams if you're doing MIMO, multi-user MIMO, the modulation coding scheme. Essentially what we're seeing is the AP taking over complete control of the BSS now, right? Because up to today, the clients decide what they want to do on the uplink. With the uplink multi-user, the AP decides everything now. The client just needs to send its packet, not do any thinking whatsoever. The AP will tell it what to do. So from an AP vendor, that's great, right? Because we have all sorts of problem with weird heuristics on the client side. So now the AP can take over, and everything's going to work much, much better. One little plug. So as I mentioned, we need the trigger to support transmission time, sync, frequency, sampling, symbol clock, power pre-correction. So all of that, the stations get off this trigger frame. So then we, once we get all the packets sent to the AP, then we need to acknowledge all that. So again, we have a multi-user coming to the access point. The access point now needs to do a multi-user acknowledgement. So we can do that in a couple different ways. .11, we like to have 5 ways of doing the same thing. We'll see in Wi-Fi Alliance what gets certified, and that will typically mean the one feature that actually gets implemented. So a couple of ways we have in the standard is that we can do a downlink multi-user transmission. So the AP can send a downlink multi-user transmission and individually address a block act to each client. That's one way. The other way is a new multi-station block act, which can then be sent in either a legacy 11A format or in a new multi-user PPDU. So there's a couple different ways. So besides the basic data frame exchange, we can use this trigger to also be a beamforming report poll. So again, I said we could use this uplink structure for helping downlink multi-user MIMO. So this trigger could be a beamforming report poll. This can be all of the compressed feedback from all the clients if we want to then do a downlink multi-user MIMO transmission right after that. So imagine with six clients transmitting feedback, rather one milliseconds in time, this is now just one 1 or half a millisecond. So a huge improvement to Downlink Multi-User Mimo by doing a parallel transmission of the feedback. And there's and then there's going to be other aspects of the amendment that we use this trigger rating for. We're going to have as I mentioned, we have a multi-user block ACK request to get a block ACK response. We're going to have a new multi-user RTS, CTS. Other reports can all be placed in this trigger frame where you want a multi-user transmission back. So it's going to be a very useful tool here for all of our uplink transmissions. Okay, so how does this work? Or how well does this work? So again, I grabbed a couple simulation slides from some presentations that were given in .11. This is from 2015. So the exact details of the simulation may not quite match, but the general concept will be accurate. We have a couple different simulations. One with 1,000 byte MSUs, so 1,500 byte packets, and then a simulation with 36 byte packet. So this is what I was talking about at the very beginning. How does performance compare with large packets versus small packets? And this is kind of start giving you an idea of when would you use what feature where. So for Downlink Multi-User, right, we have so this is the single user performance on both sides. So with large packet sizes, right, it's really best to use multi-user MIMO. Think about video streaming to multiple clients, or large file transfers. So that's the best case for multi-user MIMO, especially in higher SNRs. OFDMA, you don't get as much efficiency gain. If you already have large packets and you don't have a lot of clients, that's not really the best case for OFDMA. Now, if you have moderate SNR and then small packet sizes and a lot of clients, you're seeing almost I don't know, I always call it 60-70% gain of OFDMA over multi-user MIMO in that case, right? You're just not going to see a lot of gain if you have a lot of users and small clients with multi-user MIMO. But that's the perfect scenario to use for OFDMA. So small packets, pretty large gain especially over single user with OFDMA. Now, similarly on the uplink, again, kind of ignore all the details. Here at Scheme 1, Scheme 2. This was a presentation, when we were still working on how to, codify the technique. But similarly, on the uplink, 1,500 byte packet, you want to choose, in higher SNR, you want to choose multi-user MIMO. Smaller packet sizes, and you see OFDMA outperforming multi-user MIMO. Okay, so we did a lot of the density. We did the spectral efficiency. We're now looking at, with multi-user techniques. Now we're going to look at the other category is spatial reuse. So how do we deal with the OBSS? That's kind of in general. Right now we treat it as you defer, right? So if someone else is transmitting, you don't transmit. So what happens if you have a dense deployment? Well, like we see in stadiums, you drop everything down to 20 megahertz. You try to minimize your reuse, right? So you're capped on your network capacity in essentially 20 megahertz per BSS, right? So if you multiply that by the maximum data rate, you can get your maximum capacity pretty quickly. So how do you increase the capacity? Well, you want to go to, say, 40 or 80 megahertz. Now, the problem with that is, say, like at 5 gigahertz, if we have to drop down to, say, 5 or 4 channels, I use 4 here just because it's easier to plot, then, yes, you have a 4x increase in your network capacity from a raw spectrum calculation. But as we all know, you're gonna be blocked by all these, especially dense deployment, smaller BSS sizes. Right, you're going to hear all of these other BSSs, and so you're going to defer for all of them. So, in the best case, you would just be back to the 20 megahertz performance because you're just, using a quarter of the airtime. And the worst case is you're having collisions and all your contentions between the co-channel, co-frequency BSSs, and you actually end up worse than if you were just using 20 megahertz. And that's why we see like in stadiums or conference, the large auditoriums, we're like, okay, well, let's just use the smallest bandwidth and minimize reuse, right? So how do we address this? So again, I mentioned 802.11ah. So 802.11ah, even though it was at 900 megahertz, they were thinking about similar concepts in terms of you're going to have long transmission range, so a lot of OBSS, lots of clients. So they were also thinking in terms of how to manage OBSS differently than the typical just deferral. And so they introduced a scheme called Bss Coloring, and I have it pictured over here. So you can assign a different color per BSS. That way you can distinguish between co-channel BSSs. So with coloring, you see that you can now view that this co-channel BSS here, all these ones, are now not your BSS. So now you can have different rules based on detection of transmissions from those BSSs. And so what may those rules look like, right? So as a receiver, this can be AP or the client. You receive the signal. Is it above minus? We'll just talk in 20 megahertz numbers. So is it above minus 82 dBm? Yes. Did you decode it the preamble properly? Yes. So it's a .11 packet. It's greater than minus 82 dBm. So we added a step. Is it the same color? So yes, then that's another client in your BSS transmitting you're going to defer. If it's not your color, that's a different BSS. So now I can say, well, rather than minus 82 dBm, maybe I'll do a detection level of minus 62 dBm. The signal's coming in at minus 72. Now I can treat it as it didn't occur. So what is that bias? Well, if you're dense deployment, you're close to the AP, you've got 40 dB SNR, maybe you can handle a little bit of interference and have an SINR of say 30 dB, still get high MCS. If we can go from 20 megahertz to 80 megahertz, now this is still hypothetical, but if we could, that's 4x. Even if you take a 50% hit on your modulation coding, you're still getting a pretty big net capacity increase to your system. So that's the goal, right? We're still going to wait. We have to actually try to apply this in practice, but that's the goal, and that's what the technique in .11 is going to 11ax is going to allow us to play around with. So we're going to have the ability now, rather than have fixed detection level, to have an adjustable signal detect level. It's going to be adaptive because obviously you don't want devices that are transmitting at really high power to set really aggressive. You don't want to be transmitting at 25 dBm and then detecting at minus 62 dBm, right? So we're going to have a sliding scale. So the higher you transmit, then the more conservative you have to be. So at 20-something dBm, you'll be at your typical minus 82 dBm. Now, if you scale down your power, somewhere around 10-ish dB transmit power, you'll be allowed to detect at minus 62. So you'll be allowed to be more aggressive on your transmission if your transmit powers are lower. So that actually works out pretty well in dense deployments because we typically ratchet our powers down anyways, and so now we can kind of we can ignore the OBSSs rather than deferring. So just to kind of give you a taste of what at least simulated capability. Again, this is from 2014, so the exact parameters of this simulation don't necessarily match what we have in the standard, but it gives you an indication what we're hoping to achieve. I'm just going to point out. So this is the 5th percentile throughput. So this is kind of like the 5% worst clients in the BSS. If they were, which would be arguably the most impacted by interference. So if you can enhance them, then you have expectation of really getting a large improvement with spatial reuse. So the nominal signal detect level of -82, I don't know, in whatever their scenario was, they ended up with about 0.75 megabits per second. This, with going up to -62 dBm, they got like the 1.75, so more than double the throughput in this case. We see similarly for the average throughput here on the downlink. We're getting a from -80 to -60. We're getting over a double increase in network capacity. So that's what we're targeting, and we're hopeful for with spatial reuse. So it's actually a dramatic change in the last 20 years where we had a fixed detection, fixed CCA. All right, so this is quite a departure from that, and there's been a lot of discussions on how to deploy this, and actually even how to specify this, because in draft 1.0 there was no way for the access point to control how the clients do this, and so there's a lot of comments on, it's like, well, maybe since at the controller network level you set up your BSSs at a certain size, and we don't really want clients doing arbitrary things and transmitting it, or detecting at levels that won't fit with our plan. So hopefully there'll be a lot more control when we have draft 2.0. So that's why at the very beginning of the slide I said this presentation is on 1.0. So hopefully we're going to get some improvement to the text and spatial reuse, and then it'll be a powerful feature in the future. Okay, so I'm going to have to speak faster, I think, right? Yeah. About 20 minutes of slides to do in 9 minutes. Okay, so physical layer enhancements. So in the literature, I started seeing the term long OFDM symbol, so I'm using it here. I really don't like that. What we did is, we decided we're going to do OFDMA. You think about it, for the last 20 years, we've had 64 point FFT, we've had 48, 52 data tones in 20 megahertz. If you want to divide that up by a bunch of clients, you don't have the granularity, right? So we needed more tones in 20 megahertz to get finer granularity. If you think about it, if you wanted like at least one pilot tone per user, then you need enough data tones to amortize that overhead due to just to be able to track your phase. So we had to 64 point FFT and 20 megahertz just wasn't going to work for OFDMA. So we decided on, after a lot of simulations comparing 256, 512, 1024, we decided on 256 point FFT and 20 megahertz. You heard me mention 1024 and 80 megahertz. So it'll be a factor of 2 for every factor of 2 increase in bandwidth. But looking at 256 point FFT and 20 megahertz, we are, once we've chosen that, then that means a 4x decrease in the frequency separation between the subcarriers. So why didn't we do that 20 years ago? Well, OFDM started in 11A at 5 gigahertz. It was pretty high cost, right? We needed to give ourselves, the clocks for 5 gigahertz were costly, so on. So we need to give ourselves a lot of slop. 20 years later, we can do things a lot more cost effective, a lot more efficient. We believe we can handle frequency spacing now that's a fourth, so down to 78.125 kilohertz. What does that mean? So in the frequency domain, we decrease the spacing. That means it increases the symbol time, long OFDM symbol. So when you go, with 11A at a 3.2 microsecond OFDM symbol, we're going to 12.8 microsecond symbol. So that's the long symbol. So once we've done that for OFDMA, now what else benefits can we get out of that? We get improvement in the spectral efficiency. So we had 48 data tones in 11A and 11G. We upped that to 52 in 11N. So going from 75% spectrally efficient to 81%. In 11AX, we'll have 234 data tones in 250 out of 256. That's 91% efficient. So that's part. So that's part of the efficiency now with this new waveform. We in time, right? So we're going from 3.2 to 12.8. When we add the preamble, right? So the same 0.8 microsecond preamble that we had in 11A and 11G gave us an 80% symbol efficiency. We upped that to 89% by going to the half guard interval with 0.4 microseconds. Now 11AX, even going back to just 0.8 as your minimum, that's 94% of symbol efficiency. And then we can go all the way up to a 3.2 microsecond guard interval to handle the delay spread that I'm going to talk about in the next slide, still being the same efficiency as we had, with the basic 0.8 microsecond in 11N and 11A. So lots of benefit from changing the waveform, right? It was originally done for OFDMA, but we're getting a lot of extra benefit, and you'll see that in what we can do for outdoor. We can see that in the data rates as well. Okay, so outdoor longer range. As I said, that was one of the major goals. We are, with the new symbol structure, we can now have a delay spread within the 3.2 microsecond guard interval. So that really addresses one of the bigger issues with the typical .11 waveform is kind of the indoor preambles, indoor guard interval size. So that will really improve detection capability in longer range outdoor. We also have a feature that's TBD right now. So I can't really talk more about it, but there is a bit in the preamble that says Doppler mode. So what does that mean? Well, my hypothesis is we've had channel models for a decade now, where we have a pedestrian walking outdoors and bounces coming off fast-moving vehicles. So some of your paths now have this high Doppler. We're not addressing an individual Wi-Fi driving and trying to connect to AP. So we're not trying to do cellular mobility, but outdoors with this Doppler component to the to your received signal, then there'll be some undefined mode. Again, looking at 11AH, they had a technique where the pilots from symbol to symbol in the packet shift a position. So that means you could track the channel during the packet. So with Doppler on one of your taps of your multipath, then you can track that out during the packet. So that's not an 11AX, but since you're hearing about a bunch of things we borrowed from AH, that's possibly what could be how this Doppler bit could be used to indicate maybe traveling pilots. We'll see. So that's the handling the channel. Now the coverage, we have a new packet format called extended range. Quickly here, we have the short and long training fields are boosted by 3 dB, so that gives you 3 dB extra coverage on the short and long training fields. The signal fields are doubled in length, so you can do combining gain of 3 dB. And then, so that means your entire preamble now is 3 dB better than your normal packet transmissions. We also have a technique called dual carrier modulation. So in 11N, we added space-time block coding. That takes 2 antennas, transmit the same thing from the 2 antennas, combine it, you get gain. Here, we take 2 subcarriers, transmit the same thing, so you can do combining in frequency. So similar concept, diversity gain by replicating the data on different medium. So SDBC is spatially, DCM is frequency. So that's simulations have shown 3.5 dB gain there. Then there's a mode that you can also transmit in a 106 tone resource unit, so 8 megahertz, which means you can get another 3-ish dB of noise bandwidth gain, right? So there's a whole bunch of little features in this packet format to extend the maximum coverage say outdoors. Okay, 1024 QAM, we have 8 bits per symbol versus 10 from 11AC to 11AX. We're going from, so talk about the transmitter complexity, we're going to go from a minus 32 dB EVM to a minus 35. What's the range? We're going from 20 megahertz minus 57 dBm to minus 52 dBm detection at 20 megahertz, and then another 6 dB at 80 megahertz. So kind of give you an idea of what range we expect with that. New phi rates. So there's zillions of rates now. So rather than go through all the rates, here's a table. You have to, in your head, have to do the multiplication by the number of streams. We have up to 8 streams for both 11AC and 11AX. I've compared, say for 20 megahertz, we're going from 86.7 to 143. You'll remember you can't do 5/6 coding with 2.6 QAM and 11AC. We've got rid of that restriction, so now we have a 65% increase in gain. We have about a 40% increase in maximum data rate with 40, 80, 160. On the flip side, our minimum data rate, again, if we start addressing IoT or something with AX, these devices don't need that higher data rate. How much more time are you going to give me? I need probably like 5 more minutes. Okay, so we're with OFDMA, with the 26-tone RU, with MCS0, with one space stream, with DCM, we're down to 375 kilobits per second. So that's an IoT device, even a voice over IP, you don't need a gigabit per second, right? So if you really want a bunch of low data rate devices efficiently, that's plenty. So that's a radical departure from 11 and 11 AC of max data rate. Well, now we're at min data rate. Okay. One last section. I'm going to go through this really fast because I'm way over. Power saving. So that's that last category. So we borrowed a concept from 11AH again because they had, that was IoT. They wanted all the devices to sleep as often as possible so they could get comparable power numbers to, say, Bluetooth and Zigbee, right? So they have a technique called target wake time. Basically, the AP and the client negotiate a sleep period and then when the client's going to wake up for transmission. So rather than normal .11 where you can kind of normal power save in .11, you're asleep, you got to wake up for beacons all the time, right? If you're a sensor and you're only transmitting once every couple minutes, waking up for the beacons kills your battery, right? It's not the data transmission, it's waking up to get beacons. So we're skipping all that, right? So basically we jump down to the targeted wake time where the AP and the client negotiate. It's going to wake up a certain time. The client's going to transmit its data. It's going to receive a block act. The AP may transmit down. It then transmits block act. Done. Right. So now we get rid of all of the battery consumption from all of the management overhead that was afflicting .11 for kind of IoT devices. So that all came from 11AH. So 11AX is taking that basic construct, but now since we have Uplink Multi-User Mimo or Uplink OFDMA, it's like, well, when the device wakes up, it doesn't have to be one device; it can be a bunch of devices, right? So during this period, you can start with the trigger frame. So in this Uplink period, the AP starts the trigger frame, bunch of clients transmit, and then you continue on. So that's one change. Another change is rather than individually negotiated schedules between the clients and the AP, there's a broadcast mechanism where you don't have a pre-negotiated agreement between the AP and client. People are arguing that will scale better. Again, we have now lots of options of doing the same thing, so we'll have to see what the key will be. What will Wi-Fi lines certify, and that will dictate what actually gets implemented. So I mentioned 20 megahertz only clients, right? So now we have the permission to build 20 megahertz only, dual band clients. This was always this is always true in 2.4. But say you want, like a watch, You don't need 80 megahertz to communicate between a watch and your phone, right? So now you can build, but you may want 5 gigahertz to have a much cleaner spectrum. So this allows us to build a 20 megahertz only such type device. So the question is, how do we deal with these devices now that we have a bunch of devices that are now not capable of 80 megahertz? So we have a protocol where the 20 megahertz only devices only communicate on the primary 20 megahertz. So I plotted 40, but this extends to 80 or 160. So you can have a packet exchange of just these clients. They're in the primary. You can have a packet exchange of normal clients. They'll spread the whole bandwidth. You can mix them. So again, in a mix, you have your 20 megahertz only clients in the primary. You have your normal clients in the upper secondary. And then you can further mix and match. You can have some normal clients in your primary. You can have your 20 megahertz only in your primary, and then you can have all the rest of the normal clients in your secondary. So it's very flexible. The key is that these 20 megahertz only devices only have to operate in the primary 20. So we believe it will be a major power and cost saver to those type of devices. And last, we have a few other power-saving features. In 11AC, we had the operating mode notification that allows a client to, for various reasons, to scale down in streams or scale down in bandwidth. We have something similar called a receive operating mode. Now, 11AC, this is a management exchange, so that takes overhead, that takes power. Now, this is just a field in the MAC header of a data frame. So, as a client, I transmit a data packet. I go, subsequent packets, I'm dropping down to one stream. I'm dropping down to 20 megahertz because I want to either have interference, I want to save power because my battery is low. So I don't have to go through a whole management exchange. It's just a field in the MAC header. So it's much more efficient, both in spectral efficiency and power efficiency. Similarly, we have the same capability on transmit. Extra information is that the client can opt out of Uplink Multi-User Mimo. Say it doesn't want to deal with the synchronization and so forth. We can also use the Bss Color as power saving. You see a packet that's not from your BSS, you can choose to just go to sleep. Okay, so that helps you. Again, borrowed from 11AH, we have a bit in the preamble that says it's uplink or downlink. As a client, I know that all other uplink traffic isn't for me, it's for the AP. So if I see in the preamble a bit that says uplink, I can go to sleep again for the duration of the preamble. And that wraps up a really quick high-level overview of what you're going to see in 11AX.
Thank you for joining us for another episode of the Wireless LAN Professionals Podcast, the podcast for wireless LAN professionals by wireless LAN professionals. Be sure to follow us on Twitter @WirelessLANPros for all the latest news and updates, and also connect directly with Keith on Twitter @KeithRParsons. Head over to www.wlanpros.com for this episode's show notes, as well as the latest in all things Wi-Fi.